Okay, so welcome everyone. So yesterday we saw the phase estimation problem, correct? Algorithm for that. And what we concluded, we saw the special case and the more general case and everything. And what we concluded was that we can basically get exponential in m approximation factor using order m running time, correct? Agreed. Order m iterations of our phase estimation procedure. Correct. So now what we will see today is how to use phase estimation for this order finding problem. We will see what is the order finding problem and how to use phase estimation for the order finding problem, and then we will also see how to use order finding problem to solve factoring. Okay. Eventually we want to go to factoring. So we will have 2 hours now, 11 to 1. Then in the afternoon also we will have 2 hours, 3 to 5. Okay. Then 5:30 to 6:30 we will have the assessment. Okay. Any questions? All right. So now let us start. Okay. Okay. What is the order finding problem? Any questions so far about the phase estimation and all that? Order finding problem. Order finding problem is, we are given an integer n, non-negative integer, n greater than or equal to 1. Zn we have, correct? Remember, Zn was the set 0, 1 up to n minus 1. Now we have the set Zn star. Okay, important to note. The set Zn star. What is that? You have all the elements A in Zn whose GCD with capital N, correct, is 1. That is, they are co-prime to n. No common factor other than 1. Agreed? Greatest common divisor GCD should be 1. Now the number of elements, okay, in Z star n is what is known as this Euler function, phi of capital N. Another thing, this Z star n forms a group under multiplication. Okay, group. You know what is a group? Please raise a hand who know what is a group. Fantastic. So what we have to have is, if A and B are in Z star n, then A times B. Now remember, we will always go mod n. A times B mod n is Z star n. Agreed? If A and B are in Z star n, then A times B, it is group under multiplication. A times B is also in Z star n. Then for all A in Z star n, there exists a unique B such that A times B is 1 mod n. That is, B is the multiplicative inverse of A. A is the multiplicative inverse of B. Okay. Alright. B is A inverse. Correct? Clear? Now what is the order of A? Order A of A is the smallest r so that A to the power r is equal to 1. Okay. You keep raising to power, you get 1 Now what happens is, there is this Euler's theorem. What it says, you take any element A in Z star n, you raise it to the power what? The number of elements of Z star n, phi of n. It must be equal to 1. Euler's theorem. And order of A, so that means there is some R which will become 1. Correct? A to the R will become 1. R is the smallest such R. Order is the smallest such R. You know, A to phi n will definitely be 1. But can be something smaller also, right? So smallest such number, so the A to that number is 1, is called the order of A in Z star n. Now that order R will divide phi of n. It will be a factor of phi of n. Order of A is a divisor of phi of n. Agreed? Okay. So here there are some facts, we are just taking them for granted for now. Okay. All right. Let's take this example. Example. N is 35. Okay. A is 4. Is A in Z star n? What is the GCD? 4 and 35. GCD is 1. 4 to the power 1 is, 4 to the power 2 is, 4 to the power 3 is 64. What is mod 35? 29. Correct? Now 4 to the power 4. You will need a calculator. Correct? Huh? 250. Mod 35. What is it? Calculator. You have calculator? You can check out in your phone. 11 is correct. You did it in your mind or calculator? Mind. Hmm? 11. 4 to the power 5 mod 35. How much is that? Four to the power 5 mod 35. 9. 9 is correct. Then 4 to the power 6 mod 35. Now you can do like, 9 times 4. Same thing, right? Because you already got this 9. Now multiply by 4. 9 times 4 is 36. Mod 35 is? You could have also done like this. 11 into 4, 44. 44 mod 35 is 9. 29 into 4. How much is 29 into 4? 116 mod 35. 116 mod 35. 105, right? 11. Correct. You can also do like that. Okay. So 4 to the power 6 is 1. So order of 4 in Z star 35 is 1. 6. 6. Order of 4 in Z star 35 is 6, because that is the smallest number you have to raise 4 to make it 1. You are starting from 4. 4 is not 1. Then 2, 3, 4, 5, not 1. 6 is 1. So that is the smallest number. That is the order. Clear? Yes. Smallest power of 4 which becomes 1 when we are doing mod 35. Agreed? Good. 6. Okay. Now, what is the order finding problem? Order finding problem is we are given n and a and we want to know the order of a in Z star n. Correct? That is the order finding problem. Okay. Now how we are going to do order finding via phase estimation? You see? How we will try to do order finding via phase estimation? Okay. Now, okay, let us assume that n is anyway n is less than or equal to 2 to the n. Okay. I am saying for now, okay, you even assume n is equal to 2 to the n. Now define a unitary matrix MA. What it does, it takes any x in Zn and simply multiplies, so x goes to a times x. Simply multiplication by a. X goes to a times x. But this is all mod n. Okay. It is multiplication by a mod n. Okay, why is this a unitary? Because you see, a has a multiplicative inverse. So two different x cannot go to the same value. When you multiply by 2, multiply by a, if two things go to the same value, if I multiply by inverse, I should get back, right? How I'll get back? I cannot get back. So they must go to different values. Correct? Because a has a multiplicative inverse. Agreed? Yes or no? So it must be a one-to-one map. Multiplication must be a one-to-one map. Good. So this is a unitary. Now this is only to take care of the elements outside. You see, suppose n is not a, capital N is not a multiple, is not 2 to the n, right? So it will be a subset of 0, 1 to the n. So to take care of things outside, we just define max equal to x. That's only a technicality to take care of things outside. But we can, for now, let's forget about it. Think of capital N as 2 to the n. So this issue is not even there. Agreed? Now, we have unitary matrix MA inverse. What it does? Multiplies by A inverse. Agreed? Any questions? A inverse. Again, outside this one, outside Zn, it does nothing. Here also, outside Zn, it does nothing. Now, what do we note? For all x, if I multiply MA times MA inverse, what do I get back? Huh? I multiply by A, then I multiply by A inverse. What do I get? Same element back, no? So therefore this is identity. Correct? Yes? So this MA inverse is actually the inverse of MA. MA inverse is the inverse of MA. Any questions? Yeah? Any questions? Yes? All good? Okay. Now, okay, now remember our discussion about reversible circuits. Reversible circuits. What did it tell us? If I have this function is a reversible function, f of x equal to a times x, reversible, one-to-one function. G of x equal to a inverse times x is also a reversible function, correct? Remember our discussion about reversible functions. We will have reversible circuits for that reversible function. Yes? That means, and remember what we had said, that for reversible function we can do in place computation. We don't need BF, x, y going to x, y parity, f of x. We don't need. We can take x to f of x. Remember that discussion there? So we will actually have a circuit for this map, x to a dot x, because it's a reversible function. So for that we can do in place computation. Similarly here we have in place computation. So now you see the utility of that discussion we did, because we want to say that we need, for these are the two unitaries, MA inverse, but we need circuits for that. Multiplication is a classical computation, so we can start with a classical circuit for it. But then we all the way need to perform all those operations we did that time to get a quantum in place computation. You see that session when we did the discussion, take any classical circuit, how to make it a first reversible, then make it, if you have, get rid of the junk, and then later if it is a reversible function, how to make in place computation, all of that we saw, right? That and all will be useful here. Useful in the sense just to conclude the fact that MA will have a circuit. In place computation will be there. MA inverse will also have a circuit. In place computation. X going to a dot x, x going to a inverse x. Correct? No need any other y, this, that. Okay? You will need some ancilla, but remember? Oh, that is the state one. State one. State ket one. Okay? We will see this, okay? Once we will see this relationship, it will become clear. Now, so this is basically one written in the binary notation. Number one written in the binary notation. Okay, maybe I should clarify this. This is number one written in the binary notation using how many bits? Okay, here we are all the time talking about 0, 1 to the n. Correct. So the input wires here is, here top wires is m, below wires are n. Okay. So what do we have here? Ket1 is actually the number one written in binary notation using n bits. Using n bits. Got it? Correct. But that is basically all zeros followed by single one. Agreed? Okay. Now, okay. So, this one, as we said, is what it is. Remember this lambda m u. it used to take kx to k u to the kx, correct? K to u to the kx. Here, what is our u? Ma, which is multiplication by a. So if I do it k times, what will I get? A to the kx. Agreed? Okay. Now think of it this way. Suppose I have m. M. Think of m as for now like n, for example. Huh? Small m. Small m. So k is a number from 0 to 2 to the m minus 1. Correct? It can be large number. Correct? If m is like n, then this number can be like 2 to the n. Correct? If it is 2 to the n, how do we compute a to the power k? A to the power 2 to the power n. How many times you have to multiply? Exponentially many times. How do we do this in polynomial time? Polynomial in small n. How do we do this? You see what I'm saying? Question. I have to multiply let's say 2 to the power 100. I have to multiply a how many times? 2 to the power 100 times. How will I do that? Huh? Huh? You're saying something. Using logarithm. That is the thing. You see? What do? We first multiply a 2 times, get a square, then a square, correct? Then what we have obtained? A to the power 4. See, multiply a 2 times, you get a square, correct? Now take a square and multiply itself, you get a to the power 4. Then take a to the power 4, multiply it with itself, a to the power 8. This way you are doubling each time in the exponent, correct? So even if I have to go 2 to the 100, how many times I have to do? 100 times. 100 times, no? Each time I am multiplying 2 to 2 in, I am adding 2 to 2. A goes to a square, correct? Goes to a to the 4, which is times 2, correct? This goes to this thing square. What is this thing square? A, correct? This thing square. Agreed? We do it k times. K times. Where we are reaching? A to the power 2 to the power. Agreed? Yes? Right? So even if I have to do exponentially many, the power is exponentially large, we can still do it using only k iteration, k multiplications, correct? So that is saving us, you see. Otherwise it may not have been possible to do u to the power k for a very large k in polynomial time. But because our u is a simple thing, which is multiplication, that's why we can do even u to the power k for exponentially large k in polynomial time. Agreed? Because of this recursive multiplication. Got it? Any questions? Any questions? Okay. Okay. Now, let us do the following. Okay. So, what is the time for this? Remember, we said we can do this because k is a number from 1 to 2 to the 0 to 2 to the m. We can do it in order m recursive multiplications, correct? And each multiplication taking time at most n square, correct? Because it is n bit number. Because we are always going mod n, remember that. It is never exceeding capital N. So each time we can represent it as small n bits, correct? Yes? And then n times n square for each multiplication. It is important to remember, we are going mod n. Otherwise it would have grown very big, that number. But we are staying mod n. Agreed? So this is the time to implement this. See, eventually our m will only be also order n. So the whole thing will now, this thing will be now what? N cubed, correct? What are the eigenvectors and eigenvalues of MA? Let us ask this question now. Okay, because remember we are trying to do phase estimation. So we want to identify what are the eigenvectors, what are the eigenvalues of this unitary matrix MA. Okay, so let R be the order of A. Yes? N square is to multiply. Each time we are multiplying, no, that is n square. This is represented using n bits. A is represented using small n bits. Okay? Huh? No, not clear. What is not clear? Okay, let R be the order of A, okay? So let's try to see what is the let this vector psi j be this vector here. What is this vector? Okay, let's look at it carefully what this vector is. 1 over square root r ket 1 plus omega r. Remember what is omega r? E to the 2 pi I divided by r. Remember our convention. Omega subscript r is e to the 2 pi I divided by r. So omega r to the r is omega r to the r, this r and r will cancel, you get e to the 2 pi I. E to the 2 pi I is 1. So this is correct. Omega r is the, what did they call? Rth root of unity. Good. Now you have psi j. What are we doing here? 1 over square root r ket 1 plus omega r to the minus j ket a. Okay. Then omega r to the minus 2j ket a square all the way up to a to the r minus 1. You see this? What is happening? You have omega r to the minus j multiply by 1, 2, 3, 4 of r minus 1 and here is r minus 1. The exponent of a here is 1, exponent of here is r minus 1, same exponent is multiplied here. Clear? Yes or no? Correct? And when we say ket a, what it means? A is a number, uses binary representation, that is the ket. Always we know, right, what is ket j and all, usual. Okay? Correct? this state we are defining psi j, but the definition is clear what it defined to be. Simply start with 1, multiply, keep multiplying a, correct, and the exponent also what you do, omega r to the a minus j times a, minus j times the exponent of a, like here it is r minus 1, so r minus 1, here it is 1, so it is 1, here it is 0, so it is 0. Clear? Any questions? Then we sum all of them. Okay? This is our state. Now let us see what happens when we multiply with MA. Action of MA on this state. What MA is going to do? 1 will go where? 1 will go where? What is the action of MA? Multiply by A. 1 will go where? A. A will go where? So you see, 1 is going A is going to A square, same coefficient, like that, A to the r minus 1 go to, what is A to the r? Because r is the order of A. Correct. Now we don't know what is r, okay? So we don't know what is psi, I mean we cannot create psi j as such. Because the whole point is to find r. Order finding problem is to find r. Nobody has given us r. So as such we don't know, but we are just imagining, oh, let us say r was whatever, and let us say this state was psi j. Correct? Agreed? So when we multiply by MA, what are we getting? 1 over square root r, A, all of this stuff. Agreed? Now you can note one thing. What we will do? We will take omega r to the j out everywhere. Common factor out, omega r to the j. 1 becomes omega to the minus j. Agreed? 1 over omega r to the j, which is omega r to the minus j. This becomes minus j becomes 2j, 3j, all the way to this becomes jr. Agreed? Yes? Okay. What is omega r to the r? 1. So omega r to the r is 1, minus j doesn't matter, it is 1. Agreed? So we get 1. Now if you stare at this is the same as this. You see, 1 has a coefficient here, 1. This has the coefficient minus jr. So this is the same as this actually. You see? So therefore what have we got? Omega, this is the coefficient in front. The 1 over square root r gets absorbed here, we get psi j. Agreed? Yes? So basically what has happened, we have identified that ket psi j is an eigenvector of MA with eigenvalue omega to the j. Correct? So we have successfully identified the eigenvectors of MA with corresponding eigenvalues. For each j, different j's will give us different eigenvectors. Agreed? Now any questions here? Any questions? Omega r to the r is 1. Omega r to the r is 1. Okay? So psi k is an eigenvector of MA with eigenvalue omega r to the k. Psi k. Okay? Now what are we going to do? Now This thing we will do later in if we get time, okay. But for now let's take it for given that if you sum all these psi k's from 0 to r minus 1, what we get? Ket 1. Okay. If we sum all the psi k's from 0 to r minus 1, we get ket 1. Okay. Let us take this for granted. Now what happens? You see, the effect of this is there. See, once we are feeding okay, once we are feeding ket 1 here, the effect is that we are randomly feeding a psi k here for random k. This we will do more formally also later on. So these are all going to be like tutorial questions, but we'll do it, I mean, as we get time, okay. But point is the following, because ket 1 is summation k psi k normalized, the effect of feeding ket 1 is like you are randomly feeding a psi k. You see this? You are feeding a random psi k for a random k from 0 to r minus 1. Okay? You see this? This summation. Effect is random. So what will happen? If you are feeding a random psi k here, what is the output that you should be getting? Remember, psi k is an eigenvector of MA. Phase estimation algorithm gives us what? The corresponding eigenvalue. Correct? So what we will get here? Corresponding eigenvalue. What is the eigenvalue? What was it? Omega to the omega r to the k. Omega r to the k, correct? That was the eigenvalue. This is the same as e to the 2 pi I k over r. Agreed? 2 pi I k over r. Yes or no? So what we are going to get? K over r. Correct? That is our thing. That is our theta. That is our theta. That is our phase. Correct? Remember, the phase estimation was returning 2 pi I theta. Theta was returned. But theta was returned in what form? In a j over 2 to the m form. J was returned, remember. So j over 2 to the m is the approximation of theta that we will get. Theta is k over r. Its approximation will be j over 2 to the m, the nearest one. Agreed? Yes or no? This is what the phase estimation algorithm will give us. Agreed? Now, from here, how do we get to know? We have to find out what? R. Our intention is to find R. Remember, we don't even know what is K, because it has done it for some random K. Random K. We don't even know K. We get to know this J. Get to know the J. Our intention is to find R. So for this, we use what is known as a continued fraction algorithm. Continued fraction algorithm. Okay? Have you ever heard of continued fraction algorithm before? What does it do? Given a real number alpha, correct, and a number n, there is at most one fraction x over y with x over x and y both between 0 and n, y not equal to 0, they are relatively prime, x and y are relatively prime, and x over y is a good approximation of alpha. How good? Error 1 over 2 to the n square. Okay. So, fact. First of all, this is just a fact. This is not an algorithm. This is just a fact. What is the fact? Given a real number alpha and a number n, think of n as a large number, there is at most one fraction. Okay, we are approximating alpha. It's a real number. We are trying to approximate by a rational number. And also the rational number in its simplest form. There should be no common factor between numerator and denominator. Simplest form. Rational number in the simplest form. Then such a rational number, there is at most one such fraction. Such that both x and y are at most n. And then in which case, and there how near they are to alpha? 1 over 2n square. Correct? This is a fact. This also we can prove in the tutorial. However, given this, the point is the following. Huh? Alpha is? No, look, it's between 0 and 1. 0 and 1. Okay. So, given alpha comma n, so now this is the algorithm. What is the algorithm? Given alpha comma n, algorithm continued fraction CF will find xy, this xy, in order log n cube time. Correct? So basically, given a real number alpha, it will give you a good rational approximation for it. Rational approximation in the simplest form. Okay? And the precision is what? Precision is like 1 over n square, and the time is log n cubed. So exponential precision you can get. Correct? Yes? This is the continued fraction algorithm. Any question about it? Yes, correct. Capital N is the accuracy factor. Any questions? Okay. Mike.
Sir, is this some kind of Taylor series type function? Something?
No, continued fraction algorithm. Okay, we'll get into that. What it does is, suppose I want to find for any number this continued fraction expansion of it. What do? I first take the integer part out, then I get a fractional part, right? But that fractional part is between 0 and 1. So let's say f is the fractional part. I look at 1 over f. 1 over f. Then I again take the integer part out of that. Take the fractional part. Do 1 over that. Take integer part, like that. That is the continued, we'll see it, okay? We'll definitely see this one, okay? This is important, so at least we'll see what is continued fraction. Okay? So, that is such an algorithm is there, okay? It keeps on giving because remember we need an accuracy like 1 over n square. So, we take 2 times n. Remember we said that we can get an accuracy which is 1 over 2 to the m for phase estimate. But remember m is just 2 times n, linear in n. Still we are getting very high accuracy. That's the nice thing about the phase estimation algorithm. Okay, so what are we going to get? Any questions so far? Okay. So, what are we going to do? We are going to run the algorithm, the continued fractional algorithm, on what input? J over 2 to the m comma n. Remember what happened? We obtained j from the phase estimation algorithm, correct? We know m anyway. So, j over 2 to the m comma n, capital N also we know. We run continued fractional algorithm on this, correct? So, what happens? We get a good approximation for a rational approximation for j over 2 to the m. See, already j over 2 to the m is rational, it is not irrational, but we get a good approximation to it in the simplest form, very good approximation to it. How close? Close is 1 over 2 to the n square, correct? So, this much close approximation we will going to get for j over 2 to the m. But remember what was our fact telling us? That there is a unique approximation x over y, correct? But k over r is already this close to it, no? Remember, j over 2 to the m was very close to k over r, correct? That we already know. Then using j over 2 to the m we got an approximation which is this close using the continuous fractional algorithm. But our fact is telling us that there is a unique such things. That means it must be k over r in the simplest form, correct? That means that what the continuous fraction algorithm will return to us x over y, it must be equal to k over r in the simplest form. Clear? Yes or no? Remember, j over 2 to the m is there, k over r is there, they are very close to each other. We ran the continuous fraction algorithm to get this much accuracy. Our fact is telling us that there has to be a unique x over y which is this close to it, correct? But if it is a unique rational number, it must be equal to x over y, it must be equal to k over r in the simplest form, correct? Yes or no? Unique rational number with the values at most n, x and y both are at most n. So, bottom line what is happening? We are getting k over r in its simplest form, correct? X over y is equal to k over r in the simplest form. Okay. Any questions? Any questions? Yes? Okay. So now, what does it mean? If x over y is equal to k over r in the simplest form, y must divide r. Y must divide r. Yes or no? That means there is some, maybe there is some common factor between k and r that is cancelling, we are getting x over y. That means y must divide r. Correct? Now, okay. So, what will be our procedure? Run the entire procedure several times to get this y1 up to yl. Several different y's. Okay, remember, each time we are running the phase estimation algorithm. We are getting a y. Sorry, we first get j. J over 2 to them, we get x over y. The first one you get, call it y1. Second time run the whole thing, call it y2. Second time keep yl. Each time we are getting a y which divides r. Correct? Take its LCM. That will also divide r. Yes? Correct? If each y divides r, their LCM will divide r. Now, what will happen? We will argue later on. With very high probability, their LCM is actually equal to r. See what is happening? Each time there is a different k, by the way, because a random k. You don't even know what the k is. Only thing you know that y is dividing r. You take a bunch of them, take their LCM. That will be equal to r with high probability. Got it? That's it, you output r. So you see how we used, although several things here we have taken as facts, okay, which we'll see later on, depending on time we have. But how we are using phase estimation algorithm to find order. Yes? Any questions? So the phase estimation algorithm is the subroutine, quantum subroutine. This whole algorithm is for order finding, has a classical component and a quantum component. The quantum component is mainly to find that j, correct? And the j over 2 to the m gives us approximation for k over r, for a random k. And from then on, this rest of it, continued fraction, LCM, all that is classical. Agreed? Any questions? Yes, agreed. Shall we revise one more time, or is it clear? Revise? Huh? Clear or revise? Revise. Okay, let's revise. What happened? What is the order finding problem? We are given an integer n, this set is Zn. The set Z star n is the set of integers, set A in n, Zn, which are co-prime to capital N. The Z star n forms a group under multiplication, which means that for any A, there is a smallest r so that A to the r is 1, and that r is the order of A in Z star n. For any A in Z star n, there is a smallest r so that A to the power r is 1, and that r is the order of A in Z star n. Agreed? The order finding problem is, you are given A, you are given n, find the order of A. Clear? Yes? Good. How do we solve this problem? The way we solve this problem is, we define this matrix MA. What it does, it multiplies by A. Okay? X goes to A times X. And because we said that it's a group, right? So A has a multiplicative inverse A inverse. So therefore, multiplication is a one-to-one operation. It is not a many-to-one operation. Because if it is many-to-one, then you won't have the inverse. Agreed? So therefore, this is a one-to-one map. This is a unitary MA. MA is a unitary. Similarly, you can define this MA inverse, which is multiplication by A inverse. Now, both these operations are, these functions, multiplication by A inverse, are invertible functions. So therefore, in our discussion previously, we have seen that for invertible functions, we can get a circuit which does the computation of the function in place, a reversible circuit, x going to A dot x. So this unitary MA can be implemented using a reversible circuit in place, correct? Similarly, MA inverse can be implemented, A going to A inverse x in place. Fantastic. Once we have circuits for this, we are trying to see how we can use phase estimation. So, phase estimation. The circuit for order finding is as follows. It's pretty much the circuit for phase estimation, right? 0 comes in here. Here what comes in, remember in phase estimation we were inputting the eigenvector of u. Here we don't know what the eigenvectors are, or we don't know how to create them, because remember, even to create those eigenvectors we need to know what is R, but the whole point is to find R, so we cannot do that. What we feed in is ket1, okay, and we have this very nice and fortunate fact that ket1 is actually the uniform superposition of all the eigenvectors psi k of MA. Firstly, what are the eigenvectors? Okay, before that, okay, in order to implement this circuit, we have to argue that this entire thing is a polynomial time, correct? So we have to implement this controlled MA. What is this controlled MA? This is okay, H10 set M is okay. Controlled MA is what? Kx goes to K A to the power Kx, agreed? Because K times MA, each time MA does multiplication by A, so A to the power Kx. But now this A to the power K can be a large number like 2 to the M, correct? So how to implement 2 to the M? A to the power 2 to the power 100, how do I do? A goes to A square multiply with itself, A to the 4, A to the 4 multiply with itself, A to the 8, tuck, 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 tuck. 100 times you do, you reach A to the 2 to the 100, agreed? So that is not a problem also. So you need M iterations to at most go for any K, M iterations, because K is at most 2 to the power M, correct? M iterations, each multiplication n square time. Why? A is a n bit string. Remember, we are going mod capital N. Capital N is 2 to the power small n. So it is okay, m times n square time. Good. Now what are the eigenvectors and eigenvalues of MA? Let's try to identify that. That is important, huh? K is a number from 0 to 2 to the M. Remember, K is coming from here, remember? But this is M bits, no? So it's a number from 0 to 2 to the M minus 1. M bit number can be up to 2 to the M, correct? So if m is 100, k can be like 2 to the 100. So I have to go a to the 2 to the 100. That is, as such, if you just do naively, it will take forever. So we have to do this repeated, recursive thing. Agreed? That is, but I mean, if k is not exactly 2 to the 100, but between some powers of 2, you will do something similar. Okay? Agreed? So now what are the eigenvectors and eigenvalues of MA? Okay, so let R be the order of A. Okay? We found that this vector here, psi j, is actually an eigenvector of MA with eigenvalue omega r to the j. This vector psi j is eigenvector of MA with eigenvalue omega subscript r superscript j. Agreed? Why it is like that? Because we just said fine, okay, let us say this is the vector. We multiply by MA, 1 goes to A goes to A square, A to the R minus 1 goes to A to the R, which is 1, because R was the order of A. Right, this is where we are using that R is the order of A. 1. Now you have all this. Now what? Now you take omega r to the j out. 1 becomes omega r to the minus j. This becomes 2j, 3j. This becomes minus jr. Agreed? Now you note that omega r to the r is 1. Correct? So this becomes 1, minus j doesn't matter, you get 1. 1 and 1. So you stare at it, omega r to the minus j a, omega r to the minus j a. This whole thing is the same as this whole thing. So this is psi j essentially, 1 over square root r psi j. This is just sitting here. Agreed? We are using the cyclicity property here, you see? Cyclicity property. Now you see the connection to Simons? Simons also had a periodicity, no? You see? Periodicity, cyclicity. How people put 2 and 2 together, you see? How they connect things. The story is Peter Shor read that paper and got the inspiration. And how Simons kind of builds on Deutsch-Jozsa. Correct? So, see, we started with toy problems. It looked like we are doing some playing like a kid, right? Small problems. Deutsch-Jozsa. But that became inspiration of Simons. Even Simons still looked like artificial. But then now, order finding. That is a proper, real world thing. Okay? Okay. So we found that psi k is an eigenvector of MA with eigenvalue omega subscript r to the k. Till now okay? Good. Now, later what we will do is, we will see that ket1 we can write as this, uniform superposition of psi k's. Then what we are going to do, we are going to run, so effect of this is basically, when you are feeding ket1, effectively what you are doing, you are randomly feeding a psi k, for k uniformly from 0 to r minus 1. You don't know which k, but randomly one k is going in. Then the phase estimation algorithm will return j over 2 to the m, which is approximation of k over r. Correct? Because what is k over r? This is the eigenvalue, remember? Eigenvalue omega is the same as e to the 2 pi I times k over r. So k over r is a theta, 2 pi I theta. Approximation of that is being returned. What is approximation? J over 2 to the m. Agreed? Because of precision, we take so much precision that the precision is 1 over 2 to the n square. It's a large precision by taking m equal to 2n. Correct? Remember, we are getting 2 to the m precision. All we need is m to be 2n. I take 3n, 4n, whatever. Good precision. Fantastic precision. Now this fact continued fraction, this fact tells us what? That if I take any real number between 0 and 1, I will get this rational approximation to it, to this precision, and this rational approximation, which is in its lowest form, is unique as long as your x and y are between 0 and n. Correct? Yes? Unique. Therefore, if I am going to feed this, think of this as alpha now, right? Alpha. And what is the continuous? Okay, so what given alpha and n, this continued fractional algorithm will find this unique rational approximation in the simplest form in log cube m time, whatever. Okay? Polynomial in small n, n cubed. See, thankfully this is also n cubed, this is also n cubed. Okay? So, we find that. What was our alpha? Alpha was k over r. Sorry, alpha was j over 2 to the m. Because we are going to input j over 2 to the m to the k over r, we don't know. J over 2 to the m we are going to input to the continued fraction algorithm. It will return to us this x over y, which is the approximation to j over 2 to the m. But then we know, because this close, the only approximation possible is, the only rational number possible is k over r. Remember, k over r also has both the entries less than or equal to n. Correct? So that means x over y must be k over r in the simplest form. This is what we conclude. X over y must be k over r in the simplest form. But we don't know k. We don't know r. We need to find r. But what we notice, because of this fact, that x over y is k over r in the simplest form, y must divide r. Agreed? Simplest form, k over r, some factor is there. It cancels. You get x over y. That means y must divide r, because you divide that factor, no? Correct? Y must divide, y should be a factor of r. Huh? Which can be? No, x over y is the simplest form of k over r. K over r you have, like, let's say 12 over 20. What is the simplest form? 3 by 5, correct? So 5 divides 20, right? 5 divides 20. So y divides r. So what do? You take this y1. Okay. Run the whole procedure one more time. Get y2. Each time those y's are dividing r, correct? So their LCM must divide r. Lowest common multiple of all the y's must also divide r. Agreed? Yes? So now what happens with we'll argue separately. With very high probability, the LCM of all of this is actually equal to r. It not just divide r, it is equal to r. So we have found our r. Agreed? Yes? So this order finding algorithm has a classical part to it. The phase estimation part is the quantum part. That is to find our individual y's individual j's. From j's we find, using the continued fraction algorithm, the y's. From the y's we take LCM to get r. So there is a classical part also. Combination. Agreed? Now we'll go from order finding to factoring. Okay. Oh, this one is not updated, is it? Just give me a second. Huh? No, from where? Oh, from the Google. Google Drive. No, 11. This one, yes. We can look at the PDF. Yes, okay. All right, yes. Okay. Now we are getting into how to do factoring using order finding. Okay. So here we will have to there is some number theory involved here. Okay. Firstly, let us look at the algorithm. What is the algorithm? Input an odd composite integer n that is not a prime power. Okay. Firstly, remember we are trying to do factoring, right? We have given a capital N number. If it is even, easy to find the factor. Remember, firstly, what we are going to do, any number we will just find any one factor. Okay. Divide it, whatever is left, find one factor. Divide it, find one factor. Like that we will do. That is how we will get the prime factorization. Got it? We are only interested in finding one factor. Then we will divide and repeat. That is okay. That is the way we can find prime factorization. Okay. Now, if my number n is, I am interested only finding one factor. If it is even, it is easy, no? 2. So that is out. Okay, interesting case, n is odd. Another thing, if it is a prime power, also it is easy. If n is a prime power, also it is easy. This we will see in the tutorial. Okay. So we are assuming it is not a prime power. Agreed? N is a composite number which is odd and not a prime power. Of course, if it is not a prime power, it is not a prime number, right? Now what we are going to do, randomly choose an A from 2 to n minus 1. Simply choose randomly an A from 2 to n. Remember, this is a randomized algorithm. That's okay. Anyway, it is quantum algorithm eventually going to be. So compute D, which is a GCD of A and N. Okay, we can compute the GCD. Correct. GCD we can compute using Euclid's algorithm. Correct. Find the GCD. If GCD is greater than or equal to 2, then return. If the GCD D is greater than or equal to 2, then return D and n over D. Because you have found a common factor between A and N, right? Correct. But if it is a common factor between, remember, A is 2 to n minus 1. And if D is greater than or equal to 2, you have found a common factor which is, D has to be a factor of n also. Then you have found a factor, no? You are happy. Correct. So if A and n have a common factor greater than or equal to 2, then you are already happy. Agreed? So that is done. Otherwise, what happens? A is co-prime to n. Otherwise, A is co-prime to n. So that means A belongs to Z star n. Agreed? A belongs to Z star n. Now therefore, now you find, using the order finding algorithm, find the order of A in Z star n. That is where we are using the order finding algorithm subroutine. This is where we are finding the order, which is in turn using phase estimation and all that. Agreed? Good. If R is even, okay, you found the order. If R is even, then compute A to the R over 2 minus 1 mod n. A to the power R over 2 minus 1 mod n. Compute that one. Call it X. Compute D, which is a GCD of X and N. Okay. If D is greater than or equal to 2, again you return. Because again, if D is the GCD, if it is greater than or equal to 2, that means it divides N. So you can return D and N over D. Agreed? And you keep repeating this. Keep repeating this. You didn't get, again randomly choose. So repeat is here. Again randomly choose A. Okay. Why should this work? Okay. Why should this work? Okay. Algorithm is clear. Any questions? Yes? Algorithm is clear? Shall we repeat the algorithm one more time? Repeat the algorithm? Yes? What are we going to do? Our overall outer algorithm is what? Given we have factors n, we are only interested in finding one factor. Once we find one factor, we divide and we are into two parts. We repeat.
When we say not a prime power, that means that number cannot be written as some prime number to some power.
Yes. No, but I am saying before that also, suppose we are given any number n. What are we interested in? In finding one factor, any factor A, because I will return A and n over A. Or any factor D, let's say. I will return D and n over D. Then I will recurse. I don't even care whether D and n over D are prime or not. Okay? I don't care whether D and n over D are prime or not, because I will further factorize, no. I will factorize D separately, n over D separately. You agree to this or not? Suppose I get 20. I find factor 4. I say 4 and 5. Agreed? 4 I again find factor, no. I find 2 and 2. 5, no factor, 5. So once I found 2, 2, 5, that is my prime factorization. Correct? Yes? Suppose number is 32. I find a factor 8. I get what? 8 and 4. Then again 8 I take, I find factors. Maybe I get 4 and 2. 4 I get 2 and 2. That 4 left, again 2 and 2. So, as long as you can find any factor, it doesn't even have to be prime, you can end up with a prime factorization. Agreed or no? No, that is the subroutine we are using. I am saying, think of the outer routine first. What is the outer routine? Given an n, I just have to find any one factor. That is enough? Yes or no? Any general number n, I simply can find any one factor, and that is enough. I will repeat, to get prime factorization. Agreed or no? Now I am saying, okay, now my task is to just find any one factor. Now I get an n. I see it is a prime number. I already happy, because I have to just find one factor. I find 2 end. Correct? So as far as that subroutine is concerned, which has to just find one factor, n being prime is done. N being even is done. Because 2 is a factor. You remove 2 out, then you worry about the rest. So interesting cases when n is odd. Only then it is interesting, right? Another thing, if it is a prime power, if n is a prime power, say 7 to the power 13 or 7 to the power 20, it's a prime power. Again I can find factor. I can end up finding p itself basically. If it's p to the r, I'll find p. We'll see how to do this. It's a separate algorithm. So if it is a prime power also, it is easy. Prime power, finding the factor is easy. Okay. So we are assuming it is not prime power also. Agreed? That is the interesting case, when it is odd and not a prime power. What happened? Mike. Huh?
If a number is not a prime power,
And?
Would the number itself become a prime, or am I missing?
No, 15. 15 is not a prime power. Huh?
15 is like 3 power 1 into 5 power 1.
Correct. But it's not a prime power, no?
Oh, single prime power. Okay.
It is not a single prime to the something.
Okay. Yes.
Correct. It is not a single prime to the something. Okay? Alright? Agreed? So now we will look at this. What is our algorithm? Randomly choose an A from 2 to n minus 1. Compute D, which is the GCD of A and n. If D turns out to be greater than or equal to 2, that means D divides A and D divides n. So D greater than or equal to 2 divides n. So we have found a factor of n. Agreed? So we are done. Correct? Now, suppose that is not the case. That means A is co-prime to n. Okay, GCD we can find, that is we have this algorithm for that, Euclid's algorithm. Now we have this one. So because now A is co-prime to N, A is in Z star N. Agreed? A is in Z star N. So now what do? You find R the order of A in Z star N. Because now using the order finding algorithm. Agreed? Now if R is even, then what you do? Compute X, which is A to the R over 2 minus 1 mod N. This A to the power R over 2 also you can compute, even if R is large, remember our recursive algorithm. Correct? You compute X. Again take the GCD of X and N. If D turns out to be greater than or equal to 2, then again you are done. Because GCD of X and N, D, if it is greater than or equal to 2, it divides N. So you have found a factor of N. Okay. And then if nothing is this, you have not succeeded here or here, then you repeat. That means you randomly choose another A, repeat. Okay. What happens if R is odd? So those are the two bad conditions. What is the bad condition? That R is odd. Okay. 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 See. Okay. There will be another bad condition that will come. We'll see. So suppose we got this random choice of A which is in Z star N and its order R turns out to be even. Okay. That means what? A to the power R is 1 mod N. Agreed? A to the power is 1 mod N. That means what? A to the power R minus 1 is 0 mod N. That means N divides A to the power R minus 1. Agreed? Yes? N divides A to the power, this is the notation for saying N divides A to the power R minus 1. Now you see, we have this formula, right? A to the power R minus 1 is A to the power R over 2 plus 1, A to the power R over 2 minus 1. Agreed? Now, remember one thing. So N divides this product. Agreed? Yes? Already we are assuming we are lucky R is even. So we have R over 2 well defined. Now it cannot be the case that N actually divides A to the power R over 2 minus 1. Why? See, N is dividing this product, right? But it cannot be that N actually divides this one. Why? You see? Because if N divides A to the power R over 2 minus 1, what is A to the power R over 2 minus 1 is 0 mod N. That means A to the power R over 2 is 1 mod N. That is contradiction to the definition that R was the smallest. See, remember the definition, it is the smallest. So A to the power R over 2 N cannot divide A to the power R over 2 minus 1. Agreed? Yes or no? Yes? Good. If N cannot divide A to the power 1, now let us assume that we are lucky that N also does not divide this. Let us assume, so this is another good case for us. That is, N is also not dividing A to the R over 2 plus 1. Agreed? Now if that good case also happens, then what happens? N is dividing this product. N is not dividing individually both of them. That means N must have factors that are going here and here. Agreed? You know, n is dividing product, but n is not separately dividing this and this. That means factors of n are distributing. Agree? Now we will have GCD, will be fine. Correct? This is because the factor of n are necessarily split between this and this. So computing GCD of a to the power r over 2 minus 1 and n will reveal a non-trivial factor of n. Agreed? Yes? Any questions? You just look at it for a while, huh? Let it absorb. Mic. Oh, there's another mic also. I think this one is probably better. I don't know. Yeah.
So can you just explain what happens if n doesn't divide a power r by 2 plus 1 also?
Sorry, say again.
Can you just explain the last part when we say if we take the case that n does not divide a power r by 2 plus 1 also? Can you just explain from there once?
Okay. Let me explain. See. Okay. I have a number 15. Okay. It is dividing 25 into 9. Agreed? It is dividing 25 into 9. Yes? But 15 is not dividing 25. Suppose 15 is not dividing 9. That means what? The factors of 15, 3 and 5. Correct? They must distribute here. This is 5 into 5. They must distribute, right? Because overall it is dividing. That means 3 and 5 is present here. If you do the prime factorization here, they must be here. But they are not fully contained here, they are not fully contained here. So they must split. Now once they split, that means you have a non-trivial GCD here. Once the factors are splitting, non-trivial GCD is there. That you find, you have the factor. Agreed? Okay? Any questions? Okay, so what are the bad cases for us? Bad cases are 2. What is it? R is not even, R is odd, right? Somebody asked what happens if R is odd. Another bad case is R is even but n divides a to the power r over 2 plus 1. See, n cannot divide a to the power r over 2 minus 1 from definition of R, but it can divide potentially a to the power r over 2 plus 1. Now we will separately argue that the probability that neither of these bad events occur is at least half. So this is a number theoretic argument, separate. In fact, it is very, in fact 1 over 2 to the m minus 1 actually, where m is the number of distinct primes dividing n. Okay. Actually, the thing is that the probability that none of these bad events occur is at least 1 minus 2 to the m minus 1, where m is the number of distinct primes dividing n. That is the reason why we are choosing n to be not a prime power, so that m is at least 2. Correct? If m is at least 2, this is at least half. Agreed? Because m is 1, then this will become 0. So that's why we want m to be at least 2. That's why we are assuming it is not a prime power. And actually this fact also requires that n is odd. To argue this, the probability is at least this, also requires that n is odd. So this we'll see separately also. I mean, depends on time how much we can see, but the separate fact. So the probability that we will succeed in one loop is at least half. So therefore we keep doing it t times. The probability that we fail in each t time is 2 to the minus t. Agreed? Probability of success in each iteration is at least half. We do it t times. Probability that we keep failing is 2 to the power minus t. We want to make it delta, tiny. Then t is log 1 over delta. Correct? So suppose you want to make it a tiny number delta, you repeat it log 1 over delta times. Correct? So this gives us all the components of the factoring algorithm. Correct? Except for the fact that we have to still analyze what is the running time done for QFT inverse. We have analyzed almost everything except the running time for QFT inverse. Other than that, everything we have done. Yes or no?
For m minus.
The probability that none of these two bad events occur. What are the two bad events? R is odd and n divides a to the power R02 plus 1. If those two bad events don't occur, then we have found the factor, no? Correct. If R is even and n does not divide a to the R/2 plus 1, then we find the factor. Agreed? Yes? Now we don't find the factor if any of these two bad events occur. But the probability that any of these two bad events occur is at most 2 to the power m minus 1, where m is the number of distinct prime dividing n.
Two per m minus 1.
From where it came?
No, that is also there, but will it be a number between 0 to 1? Always doubt, sir.
Yeah, why? Yeah, of course.
M is.
This is 2 to the power m. Oh, sorry. It should be minus. I think it's a typo here. Okay. This is 1 minus m. Okay, I have to correct this. Okay. This is 1 minus m. Okay. 1 minus m. Okay. So this is the thing. Now there are a few components of it which we have yet to see. Okay, we'll start from QFT, looking at the circuit for QFT. Okay, any questions? But we will not start now the circuit for QFT. We'll do it post lunch. So were you guys able to show that that QFT is a unitary transformation that has orthonormal rows, orthonormal columns? Yes? Huh? What? What is saying? Tomorrow you will see. Oh, tomorrow you will show. Okay. But you see the connection? Order finding has that cyclicity property. Simon's problem also, that periodicity is there of S. Correct? Okay. Any questions? There is also one thing potentially, if we get time, we still have to see how we can do Grover's algorithm when we don't know the number of ones. Remember? There was this issue, right? When to stop. Because that really depended on the number of ones. Because otherwise you would have gone the other side. So that is another thing. If we get time, today afternoon, we'll try to address that also. Depending on what all things we can address. So as we have mentioned in the email yesterday, the assessment today is open book, open notes, but no connection to the internet. So you're not allowed to use laptops or mobile phone, anything, any device. So if you want to bring something, you bring hard copy. Okay. We will provide you the hard copy of the question paper. But the question paper also has the placed, so basically it is multiple choice and some descriptive, but even if it's descriptive, we give you the space to write there. So you have to write it in that space only, your answer. If you need some other sheets to do rough work, you can ask us, we will give you separate sheets also, you can bring your own sheets also. But answer you have to write there in the space provided. Okay? In the limited space provided, you have to write down your answer. Correct? And it should be all legible. Okay? Correct? Huh? Total? Total how many marks? That you will get to know. It's 1 hour. Huh? 1 hour. So printout and all, if you have to take, you have to take during this lunch or whatever it is, or you have already taken whatever it is. Correct? Do you know the place to take printout though? Huh? Huh? Food Street. Huh? Food Street only. Ah, okay. That you can take printout. Right? Ah, where? The Maggie. Okay. Correct? Alright? So by the way, you are able to see in the Google Drive there are folders now. Lecture notes, assignment solutions. You have seen assignment solutions? So I have provided there up to 5 or something like that. Because only as we are doing things I will provide, right? But assignments are there, even if you want to do homework, think about it, you have. But solutions will provide as we proceed. So till 5 I have provided. Those and all also you want to print out whatever up to you, you do. Huh? Okay. Yes. Huh? No, no. We'll stop at. We'll stop now, but then we'll go for lunch. No, modern. Everything is modern. Okay, let's start. Okay, so some people were asking, how do we see periodicity in the Simon's problem? Okay, periodicity in the Simon's problem. So what happens usually? Correct. Suppose we have f of x and x going like this. Correct. What do we have? Suppose there are different values the function is taking. Okay. Okay. Then suppose it repeats. Correct. Okay. Then again it repeats. Correct. Then we say it is a periodic function. Correct. Like this. Correct. Then this one. There is a periodicity. Agreed? So we basically the function has certain values and then we do a translation and then those values repeat. That is the periodicity. Now what happens in Simon's problem? Simon's problem, we have different values x1, x2, x3 and so on up to x 2 to the power n minus 1. Some values are there. Correct. Then what happens? The same values repeat. What is the translation? Translation is from here to here. What you do is you add. But how the addition happens? Because this is n bit strings now. In the case of Simon's, the input is n bit string. So the addition is addition modulo 2. Correct. We are in GF2 there, but it is bitwise. Correct. So that means if you add x1 plus s, you are reaching here, and the function value is repeating. Same thing here. Correct. Plus s, if you do, function value repeats. But the addition there is bitwise. When we do addition of x and s, these are n bit strings, so it is bitwise addition modulo 2. Agreed? That is the definition of addition there. Okay. Now the point is, so this is the whole repetition from here to here, correct? Agreed? But the thing is, suppose you do one more time, you come back to this, because x plus s is 0, correct? So if you do 2 times translation, you come back. So that is the periodicity. Clear? Okay. That is one thing. Not ordered. Not ordered. You can, yeah, go ahead.
I mean, not all the first values are non-repeating, and then all the repeating should come afterwards. It need not be condition.
No, no,
sir.
there is, okay, the notion of ordering here is to be taken. The point is, think of the notion of addition.
Okay.
Don't focus on ordering at this point. Because see, even the addition is bitwise addition, no. Don't think in terms, there is no like a, you are not doing a total order here or anything. Don't think of them as numbers, right? Here, because where addition is also bitwise addition modulo 2, when you're adding strings, okay? So let's not worry about the order at this point, but look at it, the translation. The translation is by S when things repeat. Then another translation by S. But the point is, this translation brings it back to this. That's all. And in case of order finding, the periodicity is, you keep multiplying by A, you each A to the R, you get 1, then you repeat. Correct? Here periodicity is 2.
2, yeah. Okay.
2. But the whole thing is translating like
Yeah.
Okay. So that is one thing. Now, okay, let us now look at the circuit for Fourier transform. Okay, circuit for Fourier transform. Okay. So, all right. So let's recall the Fourier transform. So let's do this thing. We are working with small m 2 to the m and capital M is 2 to the m. Fourier transform is given by Fourier transform of ket j is 1 over square root m summation k from 0 to m minus 1 omega m j ket k. Correct? This is the Fourier transform. Correct? Good. Now, what we are going to do actually is, we will define another transformation where, so we will call it QFT tilde, where the input j, remember input j is m bits, and this is the most significant bit, this is the least significant bit, okay. Then the output k also should have most significant bit, least significant bit, right. But we output in the reverse order, k0, k1 to k minus. You see, here the leftmost is the most significant, least significant, but what we are outputting, instead of k, we are outputting the least significant bit first, then the second, like that, and the most significant on the, at the end. So essentially, what we are going to do is, we are going to output this circuit will be for QFT tilde, okay. How to get for QFT? Simply reorder the output wires. Correct? Look, here is the least significant, most significant. What will happen here? Least significant, most significant. You just reorder. Correct? Make the topmost wire the bottommost, topmost, reorder. That will be your QFT. Agreed? So we will only see first QFT tilde. Then from there QFT we can get. Correct? Okay. Now, what we are going to do, the way we are going to construct QFT, look, this is 0 to m, so this is m plus 1 bits. Correct? 0 to m plus. So we will first assume that we have already for QFT tilde m. Correct? QFT tilde m we have for m bits. Then using this and additional gates, we will create QFT tilde 2m, 2 capital M. Correct? So we are doing QFT, this is QFT 2 to the m, this whole thing is QFT 2 to the m plus 1. So this is how we are recursively creating our QFT circuit. Agreed? We do it for 2, then we do it for 3, then for 4, then 5, like that. Yes? Good. For 2, what do we do? Firstly, we can note for QFT 2, there is only one wire, right? Only one wire. QFT 2 meaning 2 to the 1, 2 to the 1, right? So one wire. One wire, QFT or QFT tilde doesn't matter. There is no ordering issue. Now what is this? 1 over square root 2 summation k omega 2 jk, correct? Yes. But what is this? Omega 2 jk, if k is 0, it is get 0 here. What is this value? 1. What is this value? What is omega 2? What is omega 2? E to the 2 pi I by 2. What is that? Minus 1. Omega 2 is minus 1, correct? So it is minus 1 to the jk, correct? So when k is 1, it is minus 1 to the j. Agreed? But what is this? This is precisely the Hadamard of k to j, correct? So remember the remark we have made before. Hadamard transform is a special case of Fourier transform, correct? So this is QFT 2 is nothing but the Hadamard transform. Okay. Good. So this we know how to do. So base case done. So now we are going to do by induction. We know, assume we know how to do it for m, we want to do it for m plus 1, correct? Base case is done. For general m, what we are going to do, this is the circuit. These top m wires, remember we are ordering like this, least significant to most significant. The top m wires we do QFT tilde m. Then these are all phase gates, okay, controlled phase gates. We will see what they are. Controlled phase gates. Then there is a Hadamard here and this is the output. For QFT tilde 2 capital M. Agreed? Yes? Any questions? Yes? Now there is one thing we can see, that how many gates are here, whatever are the gates here plus 1, 2, blah, blah, all the way to m plus 1 gates, correct? Whatever are the gates here plus m plus 1. So what is the recursion we get? This. G of 1 is just 1, adamant, 1 gate, correct? G of m plus 1 is gm plus m plus 1, additional m plus 1 gates, correct? Let G represent the number of gates. So G1 is 1, Gm plus 1 is Gm plus m plus 1. Agreed? Yes? Just now we saw in the circuit, no? Gm plus m plus 1 additional gates. Yes? So now we solve it, it's the value that we get is Gm is summation j1 to m. Okay? Gm is summation j1 to m, which is m plus 1 choose 2, correct? So this is order m square. So order m square gates in the Fourier transform QFT 2 to the n. Agreed? Any questions? Any questions? What is Fourier transform? Fourier transform is basically a basis change. It's a basis change. Okay. What you do is, you have any function, correct? You choose a basis for functions. Okay. A basis for functions, and then you write that function f as a linear combination of those basis functions. Okay. Suppose you have a Boolean function 0 1 to the n to 0 1, or 0 1 to the n to the plus minus 1. Then for any such function can be written as a linear combination of some other functions, okay, which are the Fourier basis functions. Okay.
For example, let's say we have f n is equal to sin x, sine wave function.
Correct.
What can you say about that?
No, the sine and the cos actually form the Fourier basis functions. So you must have heard of like this for any signal, correct? You can express any signal which is basically a function, time varying function, as in the Fourier basis, correct? What is the Fourier basis? Fourier basis is the sinusoidal functions. You can always write that function as a linear combination of these sinusoidal functions, which is the Fourier basis functions, correct? Now you might have heard of this time domain, frequency domain, right? That if it is time limited, then it is frequency unlimited. If it is frequency limited, it is time unlimited. Why? Because see, these sinusoidal functions each will have a different periodicity, right? A different frequency. Now if you have a frequency limited, that means suppose you have one sinusoidal function, only one frequency, then it is not time limited, no? It goes on and on like that, correct? But if you have a time limited function, like a delta function like this, when you try to write it as a linear combination of sinusoidal functions, you will get many sinusoidal functions. That's why the time limited function will be spread in frequency. If you want to limit in frequency, then it is a sinusoidal function. But if it's limited frequency, it is unlimited in time. So basically, you are writing that function as linear combination of basis functions. Whenever you write anything as a linear combination of basis functions, that basis is your Fourier basis. And then when you are transforming to that basis, that is also an orthonormal basis in the appropriate vector space. So whenever you are transforming to that basis, it is called Fourier transform. Okay? It is basically a basis. Okay? Yes? So now, where are we? Yeah. So you can see this is a basis change, no? We are simply doing a unitary transformation. What is a unitary transformation? Unitary transformation is a basis change. It is always a basis change. It takes you from one orthonormal basis to another orthonormal basis. Correct?
That is important so that we can play with these basis states. We cannot play with the whole transform.
Yes, you need this transformation. Like how we needed the Hadamard transformation, right? So many times. Okay. So, all right. Okay. So let's see a few things. Okay. Remember, in our circuit, we are doing in the top part, except for the last wire. Last wire is J0, right? For the top wire, we have J1 up to Jm. Let's call this J prime. Okay. J1 up to Jm as J prime, which will be what? You see, you are getting rid of the least significant bit. So this is J over 2 essentially, float, depending on whether J0 is 0 or 1. Correct? Yes? And what is K prime? K prime is you get rid of the most significant bit. What is that? K minus, because you are getting rid of most significant, what is this? Km times 2 to the m, right? The most significant represents Km times 2 to the m. You get rid of that, this is what you get. That is your K prime. Agreed? Yes? Yes or no? Now, what is J? J prime, J0. In that order. J prime and J0. Okay, that means J is equal to 2J prime plus J0. You agree? J prime is the number coming from the top m bias. J0 is the last bit. What will be the whole J? 2J prime plus J0. Agreed? Yes or no? Yes? See, you have J, you have J written like this, correct? Let's say I have 3 bits, okay? Most significant, after that least significant. What is, suppose the number represented by the first 2 bits, okay, let's take 2 bits, simple case. I have say 1 0, 1 0. The number represented by 1 is what? 1. Huh? No, I'm taking the special case. 2 bits. The top bit represents the number what? 1. 1 0, I'm saying. 1. This one is 0. What is the total number? 2 times 1 plus 0. Correct? Now if I say 1 0 1, what is the number represented by 1 0? 2. Correct? Then this is 1. What is the total number? 2 times 2 plus 1. Agreed? So whatever is the number represented by the top m bits, you multiply by 2 plus J0, that is the real number. Agreed? That is what is written here. Okay? Agreed? And this one is easy to see, no? Because the last bit you get rid of, this is the most significant, that it basically represents km times 2 to the m. You subtract, you get this. Correct? Any questions? Good. No, 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 no. K is to be larger than this, no. No, no, no. K will be, K is this whole thing, K prime plus this. Okay? K is larger only. K prime is non-negative. Okay? Okay. Now, once we have done the first box there, QFT tilde m, correct? The first box, which is this. Let us see what we are getting here first. Okay? After we have done this box. So, the input for that was J prime, output was K prime, correct? J prime, K prime. So, we should have got basically this. This was the action of QFT tilde, correct? The output K prime comes in the reverse order, and then it is omega m J prime K prime. That is the, should be the intended action of QFT tilde m. Agreed? Any questions about this? Huh? Any questions? Clear or no? Yes? Now J naught is as it is, we didn't touch J naught, right? Top we only did QFT tilde m, J naught is as it is. Good. After that we are doing all these controlled phase operations, correct? Controlled phase operations. So the action of the gate is, see, if it's a controlled omega 2m gate, right? So action of the gate will be, it will just multiply with this phase. It is a control on something, action on some wire, right? So whatever the two wires, you just multiply. See, action is always on the last wire, remember? There are a lot of these things, but their action is always on the last wire. Correct? Here. Lot of these things are there, omega 2m, omega m, all the way to omega 4. Action is always on the last wire. Control is all these wires. Correct? So therefore, here omega 2m, action on the last wire J naught, control is on the first wire K naught prime. Correct? First wire, last wire, omega 2m. You see? Yes or no? See, start from the first wire. First wire is K naught prime. Last wire is J naught. The action is that you multiply by omega 2m to the power J naught K naught prime. J naught is because every time the action is on the last wire. Then next one is what? Omega m, second wire. Second wire is K1 prime. All the way up to this wire K prime m minus 1. Omega 4. Correct? Yes or no? Then this one is as it is. Remember, omega m J prime K prime was already before. This one. Already before, correct? Yes? Because all the wires is done. Yeah, correct? All the wires is done. Till now we have not done the Hadamard. The last Hadamard we have not done. This is only the control phases. Okay. Now we can see one thing. Okay, let's look at this formula first. Okay, let's recall all these things first, okay. This one we know anyways. This one we also know, e to the I pi is this. Omega is e to the 2 pi I. Omega 2 is e to the 2 pi I over 2, which is e to the pi I minus 1. Omega n is e to the 2 pi I over n, correct? Now, omega r to the Rn, what is that? E to the 2 pi I r over nr, correct? By definition. R cancel, you get omega n. Keep in mind, you can always cancel the superscript and subscript if it is multiplying in the subscript, correct? Omega 2 will be a similar formula, omega 2 to the m over 2 to the m plus 1, because you can divide, correct? Yes or no? Yes? Correct? Good. Now, so keep in mind this formula, omega r subscript Rn is omega n. We are going to use it for different values of R and n. Okay. This is m, right? We change the base to 2m. We also multiply the superscript by 2. So j prime k prime becomes 2j prime k prime. Agreed? Yes? Good. This is 2m as it is. So this is j naught k prime. Okay? What is this? M. Again change it to 2m. This becomes 2j naught k1 prime. Agreed? Again this one will be m over 2 multiplied by 4. 4. Here all the way to 2 to the m minus 1 k prime m minus 1. Agreed? Same formula. Any questions? This one is clear? What are we doing? M is there, we change the subscript to 2m because we want to make common subscript for everybody. But when we change subscript, we have to appropriately multiply in the superscript. So m goes to 2m, numerator also, superscript also goes to 2 times. This one is as it is. This one is again multiplied by 2. This one will be multiplied by 4. All the way this will be multiplied by 2 to the m minus 1. This is as it is, this is as it. Okay? Clear? Yes? Good. Now let's take J naught out here. Collect all the terms that are there here. Oh, that is already done, right? Okay. Now let's look at this thing here. Let's look at this thing here, okay? We will try to argue that that is the same as J times K prime, okay? One minute. Here. So, whatever we had put in the exponent was actually this number, okay? It was this number. Then we took J naught out, we got this number, right? Now look at this number. What is this number? K naught prime, 2k, this one all the way here, right? You are starting from the least significant bit going up to here. This is the same as K prime. Correct? K prime is this, right? 2 times K naught all the way up to 2. Yes? So that is K prime. This is K prime. So this is J naught K prime. We have 2 J prime K prime here. Now what do? We take K prime out. We get 2 J prime plus J naught. What is 2 J prime plus J naught? J. So we get J times K prime. Correct? Just simply slowly we have to see what it is and that's it. J K prime. Another thing, of course, we know minus 1 to the J is the same as minus 1 to the J naught, because when you raise to the power minus, only the whether it's odd or even matters. So only the last bit matters. Okay? Anyway, we'll come to this later. This you understood, J K prime. Okay. So we got jk prime here, correct? So we got this stuff here. Now we'll do the last Hadamard transformation. Agreed? One last Hadamard transformation is left. Hadamard transformation we are doing on J naught. Remember what was the formula? So this summation is coming out as it is. There is additional one summation introduced by the Hadamard transformation. What is it? Minus 1 to the km J naught km. Agreed? Yes? Correct. J naught goes away, it is replaced by km, and what it is now, the phase here minus 1 to the km J naught. Agreed? Good. We got all this. Now, okay, now let's look at this. Okay, this thing here, minus 1 to the km J naught and omega 2m to the jk prime. We will try to argue that it is the same as omega 2m jk. Okay, that this two together is the same as this. We will try to argue that. How? Here, minus 1 to the km J naught omega 2m to the jk prime, correct? Same thing we copied. What is this? Minus 1 to the km J naught is the same as minus 1 to the km J. You see this? Because the point is, when you are doing minus 1 to the something, the large number does not matter, only whether it is odd or even matters, correct? So this whole j thing won't matter, what will matter is j naught. Agreed? If j naught is 0, j is an even number, thus this product is even. So this thing is 1, this thing is 1, correct? Okay. Now we have this. Now minus 1 is omega 2, agreed? Minus 1, we just now saw minus 1 was omega 2. So we write minus 1 is omega 2 kmj. But now what is this? We again use the formula. Change this 2 to 2m. Multiply the superscript by kmj times 2 to the m. Agreed? Yes? Let's slowly we can see again. Minus 1, this one is the same as this because the only j naught matters. Minus 1 is omega 2. So we omega 2 the kmj. We use the same formula, change the base from 2 to 2m, multiply superscript by 2 to the m, correct? Now we have this thing and jk prime. J we take out, k prime plus 2 to the m, k prime plus 2 to the m km is k, correct? K prime plus 2 to the m km is k. So we finally got omega jk 2m, correct? And this is all in the reverse order. So now that's it, done. Okay, clear? We just have to follow the math very slowly, that's all it is. Otherwise there is no step which is very complicated, just little everything we have to follow. Any questions? So we went from m to m plus 1. So we induction. correct? 2 we did base case. So base case we have, induction step we have. So we can move on like that. And we saw that if we do this kind of induction, the number of gate turn out to be order m square. M was, remember, 2 times n or something, correct? So this is whole thing is order n square. Any questions? So now we have seen all the steps of the Shor's algorithm and analyzed the total time complexity. It is like order n cubed, but anyway you are convinced that at least it's polynomial time, whatever it is, correct? There is no exponential time step here. Okay, so now let us try to come back to some of the things that we left in between, right? We kept saying that we'll do it later, do it later, do it later. Okay. Okay, so I think okay. Okay, so okay, okay, this one you can see, right? Huh? Okay. So we wanted to argue that Z star n is a group under multiplication, correct? So let's try to do that slowly one by one, okay? First thing, let's try to argue okay. So show that the greatest common divisor of two integers a and b is the least positive integer that can be written in the form ax plus by where x and y are integers, okay. Show that the GCD of two integers a and b is the least positive integer that can be written in the form ax plus by where x and y are integers. You see? Okay. In order to find the GCD, what we can do, if you have to find the GCD of a and b, correct, what do? You try to find ax plus by where x and y are integers, remember, could be negative also, x and y. The least positive integer that can be written in this form, that is the GCD of a and b, okay. Why is it like that? Okay. Firstly, let's try to argue that GCD divides this number, okay. Okay. Look, GCD divides a, GCD divides b. So GCD divides both of ax plus by, correct? Yes or no? Yes. So therefore GCD is less than equal to this number, correct? Now let us try to argue the other way around, okay, that ax plus by also divides a and also divides b, okay. Okay. Okay, so let us say that it does not divide. Okay. So that means what? You are writing A equal to so let us say your number R was the number ax plus by, correct? Which could have been written in this form, and it was the smallest non-negative number. Let us, it was that, but it was not dividing A, correct? That means what? You can write A as R times some D plus C, correct? Remainder, huh? C is the remainder, agreed? But then what happens? That time C has to be less than R, right? Correct? Because C is the remainder. Yes? It has to be less than R. So what is happening? A times A minus RD is C, correct? A minus AX plus BY times D is equal to C, correct? Now it is A 1 minus dx plus minus yd b equal to c, correct? What happened? Now you have written another number in that form, correct? But then it is smaller than R. Contradiction. Agreed? You have written another number in the same form, ax plus by, correct? But it is smaller than R, strictly smaller than R, because remainder is always strictly smaller than R. That is a contradiction, correct? So C must be 0. There should be no remainder. Correct. So R divides A. Agreed? By condition, R divides A. Similarly, R divides B. So R divides GCD of A and B, correct? So we saw both the things. GCD divides R, R divides GCD. So R has to be equal to GCD. Clear? Yes or no? Why is a contradiction? You see, we assumed that R is the smallest non-negative number, in fact positive number, which can be written in this form, ax plus by, where x and y are integers, correct? Good. Now if R does not divide A, then you write R as A is equal to RD plus C. C is the remainder. Agreed? Now then A minus RD is equal to C. You write R as AX plus BY. You get this. Now you rearrange. You get A times something, B times something. This is another form, A x1 plus B y1 equal to C. Correct? But now it is the same form, no? And C is less than R. Correct? So contradiction. Yes? R must divide A. Similarly, R must divide B. So R must divide the GCD. Correct? Correct. Yes. So another conclusion from that is, if the GCD is 1, then the smallest possible number that can be written in this form is 1. Correct? If A and B are co-prime, then the smallest possible number which can be written in this form is yes. Any questions? Yes? Okay. So now let us go to the next one. Show that an integer A has a multiplicative inverse modulo n. Oh, wait. Sorry. Show that integer A has a multiplicative inverse modulo n if and only if GCD A times A of n is 1. That is, A and n are co-prime. Okay, firstly let us see, verify that Z star n forms a group under multiplication. Okay. Sorry, okay. So, if A and n are co-prime, then we can write this equation. Correct? Yes? Good. So suppose there is A and n are co-prime and B and n are also co-prime. Correct? Then we can write this equation. Correct? Okay. Now let us multiply. What do we get? A 1 equal to A B x x1, correct, plus A n x y1 plus B n x1 y plus n square y y1. Agreed? Multiply both. Okay, is equal to what? See, everything is mod n. Everything that we are doing is here is mod n. Multiply the two. Now, what are we getting? No, here not even mod n, here straight up even. Not even mod n, straight up. So this is equal to AB x1 x2 I will call some x1 I will call some x2 plus n times some stuff here, let's call it y2. Correct? Every time n, take n out, whatever it is, call it y2. So what did we get? AB x2 plus n y2 is 1. So that means AB is co-prime to, correct. So if A is co-prime to n, B is co-prime to n, AB is correct. Anyway, it is also easy to see, I think, not difficult to see. If A and n have no common factors, B and n have no common factors, then AB will have no common factor. No? Correct. Yes? Nonetheless, we can also see it y like this. So, Z star n forms a group under multiplication mod n. That is, sorry, one thing we have seen that if A is in the group, B is in the group, then A times B is in the group. Agreed? Yes? Now we have to also see that it has a multiplicative inverse, right? Okay. So, suppose A is co-prime to n, then we have this, yes? We can write this as A times x is 1 mod n correct. If you go mod n both sides, what do we get? Left hand side becomes ax because plus ny becomes 0, correct, plus ny becomes 0, and right hand side is 1, agreed. So x becomes the multiplicative inverse, correct. A times x is 1, A times x is 1 mod n, correct. So x is now the multiplicative inverse. Good. So we got that it is closed under multiplication and it has a multiplicative inverse. Every element has a multiplicative inverse. So that means it's a group. Okay. Later you can also try to show that this multiplicative inverse is also unique. Okay. So it's a group. Fantastic. Okay. Now, this one. Before that, let's try to do correct. Okay, this one. Suppose that we have promised that the integer n is a prime number or a prime power p to the alpha for some prime p and integer alpha. Given algorithm running in time polynomial in log n for determining p and alpha. You may assume you have an efficient algorithm for testing whether a given integer is a prime or not. For example, the Mirabin test. So, remember we in our algorithm, the reduction, we were assuming that n is not a prime power, and we said, oh, if it is a prime power, we have a separate algorithm. Okay. So what is going to be the algorithm? So we are given n, okay. Suppose it is p to the alpha. Instead of alpha, let me call it R, okay? Because alpha sometimes we think of it as a complex number, no? P to the R, okay. Now, if you see, how large can be R? How large can be R? Huh? Yeah. At most, how much it can be? How much? As a function of capital N, how much can it be? R can be capital N. Correct. You see, R can be at most log, correct, because P is at least 2, no, it is a prime. So, you are doing at P to the R, that means it is log n to the base P, which is less than equal to log n to the base 2, because P is greater than equal to 2, agreed. So, it has to be log n at most. So, now we try to find what is R. Huh? No, no, I am saying it is at most. R is what? Log n to the base P, right? Which is at most, I am just saying. At most. Okay. So, we try to find what is R. What do? We have to find primality testing we have. Okay. First we find if n is a prime or not. If n is not a prime, then R is not 1, correct. Let us go to R equal to 2. We want to find whether n can be written as P square, correct. What do? We find the square root of n. How can we find the square root? Can we find the square root? R is divisible by 2. No, we are checking if R is 2, correct. That means is it n is equal to P square, correct. So, we need to first find what is the square root. If you can find the square root, and then if it is a integer, check if it is a prime, right, then it becomes a prime power, correct, agreed. We find the square root. If it is an integer, we check if it is a prime, because we always have a primality test. Remember the Miller-Rabin test. Miller-Rabin test is a randomized algorithm for primality testing. The AKS algorithm was the deterministic algorithm for primality testing. Anyway, primality testing we have. So, given a number, we can check if it is a prime or not. So, first we check if n is a prime or not. If n is prime, done. It is a P to the 1. If it is not a prime, we are checking is it P square. So, we find the square root. Check if it is a prime or not. If it is prime, then it is P square. Then later we found cube root. Check if it is a prime or not. Go all the way to rth root up to log n. Log n is not much, agreed. Log n is polynomial in the number of bits of n. So, that will still be polynomial time. As long as we can find the rth root, as long as we can find the rth root, it is still polynomial time, agreed, because primality testing is also polynomial time. So, to find square root, we can find using some, for example, Newton's method. Okay. Pardon me? Why? Sorry, for what you mean? Okay. Okay. No, the point is we should be able to find the square root, right? Correct. So you can go and read up how to find rth roots. Okay. For example, you can use Newton's method, correct? To find the root of a polynomial equation, right? Suppose I have x to the r, the equation x to the r is equal to n. I have to find x. So maybe use Newton's method for that. Okay. So anyway, we can find rth roots. Once we can find rth root, we can do this. Correct? Clear? This becomes polynomial time. If we can find rth root in polynomial time. Agreed? Any questions? Yes? So this was one of the part. Now let's get to this one. Okay, let's get to this one. Before that, let's get to yes, Fourier transform. Okay. We want to verify that this is a unitary matrix, correct? So orthonormal columns, let's verify orthonormal columns. What is the inner product of the two columns, first two columns? Summation j 1 over m going from 0 to m minus 1 omega m to the j. Agreed? This is the one? Yes? Okay. So what is this? These are the different mth root of unity, correct? Omega m was e to the 2 pi I over m. So this is the one mth root of unity. You can get different mth root of unity by doing this. Correct. Omega j to the this one, omega j m to the m is what? Omega m j m, correct? Which is omega m to the j, which is, so all of these are different roots of unity, mth roots of unity. And if you sum all the mth roots, okay, you can verify, this is a formula, this is a standard formula, they sum up to 0. Because of the symmetry, you see, the roots are like symmetrically placed on the circle. You add all of them, they are 0. Okay? Correct. What are the two roots of unity? Two square roots of unity. 1 and minus 1. Correct. Add up to 0. 4, the fourth roots of unity, 1i minus 1i minus I. Add up to 0. So all these roots always add up to 0. They are symmetrically placed on the circle. So this is 0. Okay? In fact, we have a more general formula. Even if you multiply by k, but k is non-zero. If k is non-zero, then also that is 0. Okay? K is 0, then of course everything is 1. But other than that, it is 0. So therefore, if you look at all the any different columns, you multiply, you will get a summation of this kind, where k is non-zero and will be 0. If you take any column and itself, you will get a summation of this form where k is 0. You take this column, multiply with its by the way, there is one thing we have to little careful of. When we take product, we take the column and multiply with a conjugate of this, correct? So if you, okay, so let's say you take two columns, okay? You take two columns, what are you going to take? K1 omega m minus j k2, agreed? You will get like that. One column will be k1, other column will be k2, but we have to do conjugate, so minus. This becomes summation over j omega m j k1 minus k2, correct? Agreed? But when you k minus k1, if k1 and k2 are distinct, this goes to 0, okay? Is equal to 0 for k1 different from k2, is equal to 1 for k1 equal to k2, correct? Yes? Clear? Any questions? Yes? Yes? So that is one thing. Yeah, let's come here. So this one we have already seen, right? Why these are the eigenvectors with corresponding eigenvalues. Psi k's were the eigenvectors MA with corresponding eigenvalues omega RA. Correct? This we have already seen in the model. Now we wanted to show that this is 1. Agreed? Remember? Okay, let's do that. Okay. Now, summation k is equal to 1 over square root r summation k, and then there is a summation j, correct? Agreed? Correct? This one, this summation here, we wrote as the inside summation. Correct? And the, okay, then there is also more 1 over square root r. So there is this. Agreed? This summation over k, then the inside summation is over j. J is increasing from 0, 1, 2 all the way to r minus 1 and a to the r. Correct? Yes? Correct. Now, again same thing, you see? Same thing. J equal to 0. What is j equal to 0? Get 1. Correct. Get to the a to the 0? 1. What is this? Use this formula. If, okay, let me write this little bit. 1 over r, exchange the summation, okay? J equal to 0, r minus 1, k equal to 0, r minus 1, jk, a to the power j. Agreed? We just collected the sum inside. Now j equal to 0, what is this? Huh? This, and there is r. Correct. What is this? This is r cancels, you get 1. Correct? J is not 0, what happens comes? 0. Same formula. Correct? J is not 0, you are summing over k, this thing is 0. Right? So you just get this. Okay. 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 Now let's try to look at this one. Okay. In the phase estimation procedure of order finding, we start with the state Ket1. The state just before the measurement when we run the phase estimation circuit on Ket1 is this, where psi k is the state of the first m qubits that you would get by running the phase estimation circuit just on psi k. So remember, if we are putting psi k in the phase estimation circuit on the below wires, let us say the state that occurs on the top wires just before the measurement, let's call it phi k. Okay, phi k. So then what will happen when we are inputting Ket1, the state we will go to, because this is the summation, this is the state we are going to get on the combined wires. Yes or no? Yes? If this state, starting state, with k we get phi k. So this will be the superposition. Agreed? Now show that the probability of obtaining some value j on running phase estimation on 1 is 1 over r summation k from 0 to r minus 1 probability outcome j on running phase estimation on psi k. Correct? Yes? Yes? Yeah? When we have some state phi, okay, probability of measuring 0 on this state phi is what? Hmm? Hmm? Sorry, probability of obtaining any j on this state is what? Inner product, right? Inner product j mod square, correct? What is this? Mod phi and its star, correct? Right? Yes? Correct. Hmm? So now we are trying, there is this phi star here, right? Phi star is the state on the top wires and the bottom wires. We are only doing the measurement on the top wires. So if we look at this, we are not doing anything on the bottom wires. So this tensor identity. Okay, doing nothing on the bottom wires. Then phi star, and same thing here. Okay? If you want, you think it like this. Okay? Agreed? This will be the probability of obtaining J. This is the probability of obtaining J on phi, right? But we are trying to find what's happening on phi star. This will be the probability. Yes? Correct? Because we are doing on J, nothing on bottom bias. So we are representing doing nothing on the bottom bias by identity. Correct? Yes? Now let's do that. What is it? This is summation. Okay, let me take that 1 over r out. Summation k phi k psi k, correct? Times summation, let's call it L, phi L psi L, correct? Yes? Then J tensor identity. Agreed? Yes? Yes? Okay? Hmm? Sorry, what? Tensor on? Tensor on I. Because this is the bottom bias. Yeah. No, no, it's always tensor. The space is in tensor. The space is in additional wires. Whenever you have additional wires, it's an extra. No, combination will be. No, no, this phi star. See, phi star is in n plus m wires. Phi star is in n plus m wires. Correct? This is in the top m wires, this is in the n wires. This is n plus m wires. Okay? Yes? Okay. Maybe let's do it the other way. Yeah. Let's do the other way. Yeah. Yeah. See, okay. Remember one thing, this thing here is a scalar, correct? This thing is also a scalar, correct? Scalars float freely. So let's rewrite in this order. Phi star J tensor identity, then J tensor identity phi star. Okay? Let's do it this way. This becomes, now let's do summation k, I'll take 1 over r out, summation k phi k psi k, correct? What is this? J with J. So that is J with J, tensored identity, correct? Then summation L phi L psi L. Agreed? Yes? Now let's collect the terms. 1 over r summation. Remember, if this k is different from L, what is happening? Psi k psi L, right? There is a psi L here, right? Psi k and psi L with identity gives you psi k inner product psi L. What is that? What is that? 0, because eigenvectors form an orthonormal set. Agreed? Psi k psi L is 0. So only k equal to L is remaining. Correct? K equal to L is remaining. What is it? Psi k, phi k with J, J and phi k, correct? This is remaining. What is this? This is the same as this. If I do for k, this is the same. Remember? Look here. I don't know whether you guys can see it or not. There's a J here, right? Okay? Sorry. It's like this. The J is this way here, correct? And a J. Agreed? Yes? But what is this? This is also a scalar, this is a scalar. They float freely. This goes here. This goes here, this is exactly this. Correct? This one, if I put it here, it's exactly this. Correct? What is this? This is equal to probability obtain J on input psi k, right, on the bias below, correct? This is the probability to obtain J on the input psi k in the bias below, on bias below, correct? Yes? Let's call this P J K, correct? So this is equal to 1 over R summation K P J K, correct? So it is basically as if a random K came in the wires below, agreed? Yes? Okay, clear? Okay, so I was going to mention to you about the continued fraction algorithm, correct? Continued fraction algorithm. I erase this. Let's say we have 1.5. What are we going to do in the continued fraction algorithm? We'll write 1 plus 0.5, okay? Take the integer part, fractional part, okay? Then what happens? This we write as 1 plus 1 over 2. Now it's done, right? Because at 2 I don't have any fractional part. If I have fractional part, I would have continued. Now it is done. Agreed? So what do we get here? This is 3 over 2. Yes? Agreed? .3. Okay? What is this? 1 plus 0.3. This is equal to 1 plus 1 over See, what is 0.3? 3 over 10, right? So we write as a 10 over, agreed? 10 over 3. Now this is 1 plus 1 over, how much it is? 3 plus 1 over 3. Agreed? Yes? Now I don't have to continue. Correct? I don't have to continue because one over 3, correct? This has no fractional part. Yes? So what is this whole thing now? Whatever it is your answer. What it is? 1 plus 1 over, I mean eventually it will turn out to be 13 over, what is it? 13 by 10. No big deal. Correct. Huh? But the point is, this is how you get the, you see how the algorithm is working. Okay, now let us say okay. Suppose we have 1.333333 infinity. Okay. What do we do now? 1 plus, 1 plus 1 by 3, right? But if you follow this algorithm, we have 33333 like this, correct? So yes, but anyway we will write this as the fraction, so we will get this, correct? But anyway you understand the procedure, right? Procedure is, when you have a number, correct, it has an integer part and a fractional part, correct? So there is an integer part, let us say 2 point some fraction f, okay? So we will write it as 2 plus 0 point f, correct? But we will try to express the this fractional part would be 1 over something large, 1 over 1 over point f, correct? Yes, but this is a large number now. Then you recurse and keep going on. At some point you stop, and that is your rational approximation to that number using continued fraction. Agreed? Yes, this is the algorithm. Now this algorithm gives you a good rational approximation. Okay, it gives you a good rational approximation very fast. Let me try to see some more non-trivial example of this one. Okay. So let's see. Okay, let me just, try to write this. 2367 divided by 1700. Okay? Huh? By the way, let me also mention Euclid's algorithm for finding GCD. How does Euclid's algorithm work? Let me mention that first, okay? Okay, let us say you are trying to find GCD of A and B, okay? Yes? Assume A greater than B, okay? So what do? You write A as B times quotient plus remainder, okay? You can write like that. Now this you have found, okay? Now you repeat with B comma R, because B will be larger than equal to R, so repeat, correct? Now you keep doing this until remainder becomes 0, and at that time whatever is the B, that is your GCD. Okay, keep doing this. Let's do this actually, okay, on an example. Okay, 2307, and we are finding the GCD with 1700. Okay, so we write this as 1 into 1700 plus 667. Okay, good. Then we are repeating with these two, right? So 1700 we write as 2 into 67 plus 366. Okay? Then we're repeating with these two. 667, 1 into plus 301. Okay? Then repeat with this. 366 equal to 301 plus 65. Okay? Then 301 equal to 4 into 65 plus 41. Then 65 equal to 1 into 41 plus 24. 41 equal to 1 into 24 plus 17. Okay? 17 equal to 24. 24 equal to 1 into 17 plus 7. 17 equal to 2 into 7 plus 3. 7 equal to 2 into 3 plus 1. Then 3 equal to 3 into 1. Zero. Correct? Right? What is the GCD? 3. You see this? Correct? Euclid's algorithm. Now, actually, if you see, there is a close connection between this, okay, I'll erase this, okay, and also the continued fraction. Huh? What? What is it? You want to run another example? Yes, 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 yes. A comma B. Yeah. A comma B, right? So the B at the, see, okay, the last equation was 7 equal to 2 into 3 plus 1. Now we are repeating it for what? 3 comma 1. Correct? Eh? Yeah. So 3 equal to, see, it is the B comma R when R becomes 0. Correct. So next time 3 becomes 3 into 1 plus 0. So the new B comma R is 1 and 0. R is 0, B is 1. B is 1. That is your GCD. You're right. The GCD is 1. Let's run it on an example. Okay? Let's say, I don't know, GCD of 18 and 21. 18 and 21. What is the GCD? 3. Okay, let's see whether we get 3. So 21 equal to 1 into 18 plus 3. Okay? So we repeat it on 18 and 3, correct? 18 equal to 6 into 3 plus 0. So 3 is the answer. Yes? Okay, so this is, by the way, the continued fraction, okay, in the continued fraction for this, what happens is this. Two, 3, 6, 7 divided by what was it? 1700 turns out to be 1 plus 1 over 2 plus 1 over 1 plus 1 over 1 plus 1 over 4 plus 1 over 1 plus 1 over, it goes on like this for long. But you know what happens? There is a very nice connection between the continued fractional algorithm and the Euclid's algorithm. Connection is these things that you are getting right are precisely going to be the value of the quotient that you keep getting in every iteration in Euclid's algorithm. This thing that you're getting 1 plus 2 blah 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 is precisely the quotients you keep getting in that Euclid's iterative thing. Anyway, so now it's time for us to stop. Okay? All right, we take like a half-hour break. Okay? Then we come back.